All right, so from Alex, we have IQ scores among the general population have a mean of 100, a standard deviation of 15. A researcher claims that the standard deviation sigma of IQ scores for females is not equal to 15. A random sample of 28 IQ scores for female had a mean of 98 and a standard deviation of 20. The IQ scores for females are approximately normally distributed. Is there significant evidence at the 0.1 level significance to conclude that the researcher's claim is correct? And I'm going to ignore their kind of step-by-step here and just, you have a blank page and you had to do all 5 steps to the hypothesis test. What should you be doing from here? So the very first thing thinking about for this, start writing down the information they give you. All right? So as you read through the here we have IQ scores, have a general population, have a mean. So I know that the mean for the population is 100 and the standard deviation is equal to 15. So that's just statement in the first part. A researcher claims that standard deviation, sigma, is not equal to 15. So that's their claim. That will help me later. A random sample of 28. I know n equals 28. Right? So as you write these, it'll narrow down formulas in what you're doing when you're writing out what each number stands for. So this mean and standard deviation are in the same sentence as that sample size of 28. So those are going to be the sample mean and the sample standard. So to keep those apart, they're in the same sentence talking about that random sample. Now, assuming their IQ scores are normally distributed, this has to do with the sample size. So anytime your sample size is less than 30, this doesn't kick in unless you have a normally distributed population to start with. But we're not going to use the normal distribution anywhere in the problem. That's just an assumption that you need to, in order to use the t distribution, the chi-square distribution, or the f distribution, anytime you have a small sample population itself needed to be normally distributed. The sampling distribution, the distribution of x bar, the distribution of s, those kind of things are not normal. Those follow the t or chi-squared, etc. So we can really ignore when it says the assumption. Sometimes that'll help you with things, but we don't need it. This piece right here gives us alpha. So we have alpha equals 0.1. That's our level of significance. So with that piece, then go to your flow chart. And think about, my claim was about a sigma. It was about a standard deviation. On the left, proportions, means, variances, or standard deviations. So here I have standard deviation. Do I have one sample or 2 sample? If I go back here, I only had 1 sample to deal with. They gave me a population, but that's not a sample. I only had 1 sample here I'm working with. So I'm going to go up to 1 sample, and it says, here's my test statistic, here's how I'd write my null hypothesis, and here's the shortcut program on my calculator. Going through. So my hypothesis and my null is going to be the, in this case, sigma equals rather than sigma squared, but you can write it either way. So we have our hypothesis statements. My claim is that they're not equal, and the not equal sign is only allowed in the alternative hypothesis. So that's my claim in the alternative. The complement to that then would be that sigma is equal to 15. Now, if you wanted to write it in, oh, my calculator's stuck. There it is. As a variance, that's fine. If I were to take 15 and square it, it comes out to be 225. These are testing exactly the same thing. And I don't care which one you use. I would assume it's easier just to stick with what you have given in the problem. So we're going to use this sigma equals. And the formula for this test statistic is already stated in that flowchart. So I have my chi-squared n minus 1 times s squared all over sigma squared. This is the one I said just be really careful. If they give you a variance, don't square it again. That kind of thing. So they give us standard deviation, so we just are putting it in for s and sigma. If you have a variance already, you don't want to square it. N minus 1 would be 19. That's oh, sorry. I'm looking at the wrong number. N was 28. It would be 27 times s squared. S was 20. And then the sigma comes from your hypothesis statement. So that's another thing to keep in mind is that, like, let's say I gave you raw data and you just plugged it into 1 var stats. And you found x bar, s, and there's a sigma that comes out in that 1 var stats. You would never write that down because that's a sample you just put in your calculator. You didn't put the population in your calculator. So if there's a sigma in the formula, it's always coming from something that was already stated in the question. Now, I don't know what that equals. I can get that information, though, off of that SD-infer program. If you have raw data, you would need to run one var stats so that you have n and you have s. So we're actually not going to even use the sample mean here. This question wasn't about means at all. It was about the standard deviation. So it's just extra information that they give you in here. So if you go into programs, and SD-infer, I have more programs probably than you guys have on here. SD-inference, if you're on the TI-83 older style, you have SD-infer 83. Enter to start the program. S would, now this again, be careful. If they give you the variance, make sure you put square root of whatever value that they had in here. N was 28. We're not going to do these top two. Those are confidence interval for a variance or standard deviation. That's something we dealt with in 243, or some people did, depending on your class. So we're only going to do option 3, 4, and 5, which is the left-tailed, two-tailed, or right-tailed test.
When you're putting an S, do you have to compute the square root if you're doing the variance beforehand, or can you put in the square root?
You can put the square root symbol right in there. Yeah, you don't have to compute it. You can either way, but go out at least like 4 decimal places. If you round that too much, then your answer will be off quite a bit. All right, and we had not equal for our alternative hypothesis. It's going to ask you the value for sigma. And again, just be careful if they give you variance already, put square root of whatever they have in there. And where it says chi-squared equals 48, usually it doesn't come out to be a nice integer like that. Yeah, it is. I just, that they probably cookbook those example problems up to come out. Usually it's a decimal, so go out 4 decimal places. And then right below that, what's great, it gives you the p-value. So our p-value is 0.0154. Alpha was 10%, 0.1. Be careful with that one. Oops. So 1.5% smaller than 10%. P-value is less than alpha. We would reject the null hypothesis. And again, if you forget your rejection rules, on the very top of the formula packet, it gives when to reject for p-value, critical value, and confidence interval.
I ran into this problem a few times, like in the work in the labs. If you get a p-value that's exactly 0 or 1, should that be an indication that you've done something wrong?
If you get a p-value exactly 0 or 1 on a calculator or in Excel, what's happening is it's not actually 0. It was just so many zeros in the decimal places that it rounded it to that value.
I tried to go now to like 15 decimal
Yeah.
places.
So just as a general, in my class at least, you should never get one that rounds to 1. Yes, you get them to round to 0 all the time. So if it rounds to 1, that would mean that you were thinking about, usually that happens in a one-tailed test, but it doesn't have to, but that means your test statistic, oops. Your test stat was way out here, and you're saying that all of that is your p-value. So you got a really large positive test statistic, but you were doing a left-tailed test, and that's really odd. So most of the time, not always, but anytime you're thinking like, here's my mean, and I'm trying to do a left-tailed test, usually that test statistic is going to be a negative number. When you're doing a one-tailed test on my exams, they will match the sign on a z and a t. Chi-squared and f's are different because they're always positive. But if you're looking at a left-tailed test and you get down to your test statistic and it's positive, something's wrong. Either the sign here is wrong, or you messed up like maybe the direction of x bar and mu, something like that. But it is common sometimes to get, let's say we got a t of a negative 25, way out in the tail. There's so little area. Most of our t's are between negative 4 and 4. So there's so little area that p-value is less than 0. You just found a huge difference in the hypothesized value in your sample data. And that's really common right now. Like, for instance, last year, the Journal of Behavioral Science no longer uses p-values at all. What they do is they look at the actual confidence interval that tells you in the same scale as your data what that difference would be. So not worrying about, like, if you take of a p-value of 0.000 and 0.01, we can't say that one is more significant than the other. They're both significant statistically. But what the confidence interval does is it gives you more of a practical evaluation. It gives you the difference between statistically significant and practical significance. All right, going through. And I've used this example before, but if you are trying to find a route to work that's faster, and you go one route that's beautiful, has scenic, has the osprey along your bike path and all this stuff, and statistically it comes out that there's a significant difference by taking the car route, but practical significance, it only saved you, let's say, 1 minute. So is it worth the stress of traffic to go through all that because I statistically saved 1 minute of your time? So you have to look at practical significance a lot, and I think a lot of p-values ignore the practicality of things going on.
Is that a confidence interval method?
Not for the variance and standard deviation, but yes for the two sample tests. There's a confidence interval method to match them, and I think I have brought one of those too. Well, this one didn't ask for that, but we could use that same data. This is another Alex problem. So let's go ahead and put these two data sets into the calculator. In list 1 and list 2, but I'll read it real quick. We have, according to a high-profile realtor, houses in the sleepy town of Sun Beach have shown higher appreciation over the past 3 years than have houses in the bustling town of North Arden. To test the realtor's claim, an economist has found 10 recently sold homes in Sun Beach and 10 recently sold homes in North Arden that were owned by exactly 3 years. The following table gives the appreciation, which is expressed as a percentage increase for each of the 20 houses. And we're going to, instead of doing a hypothesis test, we're going to do a confidence interval. So all I'm going to do is enter that data into the calculator real quick. So in my list 1, I have, let's see if I can get this to, it's only focusing on one. 12.6, 12.1, 11, 11.9, 9.2, 9.5, 11, 10.9, 9.5, and 12.6. And then for North Arden, we have 10.3, 10.6, 9.7, 9.3, 10.3, 11.8, 8.6, 6.9, 9.8, and 7.5. Go ahead.
Sorry, do you have to have two data sets to use the confidence interval?
No, but one sample confidence intervals was really what we did in 243, so I'm not going to test it in this course I'm going through. But you can do the confidence interval method for one sample and still work the same way. It only matches to a two-tailed hypothesis test, though, so they were asking for a one-tailed on this one, but we're going to just change it and just do the two-tailed, looking for a difference or not a difference. So in this, on this exam, you're going to have a hypothesis, and it's, oops, sorry, I'm off the screen. And you're looking at two means for the independent groups, or the difference in the means for your dependent groups, or you have two proportions. That's when you're going to be using the confidence intervals. And there's formulas for each one, but this one is going to be two samples Z or T interval. This one is just called the T interval, but it's on the difference between the two groups. So you subtract group 1 minus group 2 for each pair, and then do that T interval. And then this is the two prop Z interval, it's called, two proportion Z interval. With each of these, they can be rewritten. So I could look at mu1 minus mu2 equals 0, rather than mu1 equals mu2. If two things are equal, the difference between them has to equal 0. If two proportions are equal to one another, the difference between them is equal to 0. And this one's already set up to equal to 0. So kind of 0 is our magic number. We're talking about, is 0 in the confidence interval? If we have yes, then our decision is do not reject the null. If 0 is not an interval, that means both of your boundaries are both positive or both negative, then our decision would be to reject the null. The null is the 0 part, right? If it's not equal to that, then you would have reject. So if I wanted to take that data set and what was alpha? Alpha was 0.1, so I'm going to say let's find the 90% confidence interval. And this one was talking about means. Go to your flow chart. Oh, it was asking a lot. We're going to kind of ignore what they were asking for.
Oh, okay.
And we're going to just find the confidence interval for now. Yeah, because they're asking higher than one or the other. If you wanted to set up, but they're looking at Sun Beach was group 1. And North Arden was group 2. So I'll just put your 2 labels on there and then ask yourself, which one do you want larger than the other ones? Sun Beach has shown a higher appreciation, so Sun Beach should be bigger. So be careful with those 2 groups, because just because you see the word higher than doesn't mean automatically a greater than. It depends on which one comes first. Well, they're actually then setting this up, if I look at the hypothesis test for this, would be about the different means. So I have group 1 is Sun Beach, group 2 is North Arden. They're independent, right? And that's hard to see sometimes. On the exam, I actually do put the word dependent R, assuming everything else is independent. But they didn't say like the same builder and lot size or anything like that. They're not matched up in any way. Yes, the sample sizes are equal, but they're not matched or paired up in any way. So these are independent t-tests. And that might help, again, with the flow chart. I'm looking at means. So here your flow chart is on the left. Samples of data. They're independent because there's no pairing that goes on there. I don't know what the sigmas are. There's no population standard deviation given, I don't think. Was there? Yes, no population standard deviation was given, so sigmas are unknown. And then if you go here, it'll help you set up your hypothesis statement, right? We have mu1 or equal to, or greater than or equal to mu2. And it tells you which hypothesis test to use, or in our case, which confidence interval to use. So here's your 2 sample t-int that we would want to use for the confidence interval evaluate. So they're looking at this as a right-tailed test. If you were to complete the problem they were asking for. We're just going to practice real quick with the confidence interval instead and do the 2 samp t interval. I have that data in my calculator, in list 1 and list 2. So I can go to my stat menu, I can go to tests, and in the TID9, your interval menu is way down, or is way over on F7. It's not in F6. So we have to go down quite a ways to get your confidence intervals. I skipped it. So option 0 on my calculator, 2 samp t-int. We have raw data, so I want data highlighted. I have it in list 1 and list 2. Frequency is always left as a 1. We want to match our confidence level, because they say 10% for alpha. We'll use 90% confidence level. Again, please use the no. Alex may ask for yes when you're going through. Do calculate, and it gives you your answer. And I would prefer you use the notation that the calculator gives you, or this notation. But the calculator one's probably easier. You get that parameter wrong in the middle, I'm going to take points off. So if you put an X bar or just 1 mu or something like that. If you just give me the parentheses, I'm fine with that. Oops, that wasn't negative, that was positive. 0.47692, comma, 2.26231, 26231. And then in parentheses, I'm fine with that notation. Then you don't have to worry about what parameter should go in there. Right? If you have 2 proportions, it's going to be P1 minus P2, that kind of thing. If you have dependent groups, it would be a mu D in there. All right, now looking back, is 0 an interval? they're both positive, so 0 can't be between two positive numbers. You've got to have a negative on the left and a positive on the right. So 0 is not in there, so we would reject the null. And then you can conclude, right, that there is a difference between those appreciation rates. That's how you'd apply. Another thing I might ask is interpret the confidence interval. Like, what does that mean in the context of the problem? So real quick, I know we're out of time. I got a meter problem myself here real quick. But if I asked you to interpret that value as a 4, don't forget to put your confidence level in there. So one can be 90% confident that the difference, you should have average or proportion in here, depending on the context of the problem, right? We were talking about averages. So the difference of the average, and I want to go back to what they were talking about. What's my variable name? It was the appreciation rate between Sun Beach and North Arden is between 0.4769 and 2.6231. What's our units here? There, it just said percent, so those are each a change in percentage. So if the units were back in inches or seconds, make sure you put that unit time back in there. So sorry, I'm going to have to run.
You don't have time to update.
Oh, yeah, I can do that. Just do a quick update your operating system.